Hello, everyone. My name is Antonio Vallasoler, and I'm analyst in the Nuclear Technology Development and Economics Division at the OECD Nuclear Energy Agency. It is my pleasure to welcome you to the second day of the NEA workshop on advanced construction and manufacturing methodologies for new nuclear build. For those that did not attend the workshop yesterday, I would like to provide a brief summary of the discussions that we had. Yesterday, during two sessions, we explored recent and ongoing large reactor construction experience, and also we had a focus on a specific construction and manufacturing techniques. Especially what we learned in session one is that digital engineering is clearly the way to de-risk construction, but also is a way to accelerate specialized learning in complex environments where there is high turnover. Modularization in large reactors is possible and makes sense specifically in dense and interface regions of the design where there's a critical path. Aspects like access to the site, layout, crane optimization are also important, as well as cultural differences in the practices of construction. More important than digital engineering and other new construction strategies is the need to complement all of this with robust project management practices, trust, clear distribution of responsibilities to ensure the overall success of the project. And also important trade-offs between replication and design optimization are necessary. It is possible that replicating a non-optimal design can be a good approach since it is difficult to anticipate the impact of small changes in complex systems. In session two, really, when it comes to digital engineering, it is important to make additional efforts to ensure that we achieve full digital continuity between the design and construction phases, and that we have robust standards to interoperate between tools and softwares. Also, there are major and proven construction techniques from other sectors, such as steel plate concrete structures or vertical shaft that are already delivering promising results. Now, the idea is to make sure that we measure the impact in nuclear projects, and this is already happening in demonstration test beds. Reducing the size also with SMRs is a good way of reactors is a good way to explore new manufacturing and construction techniques. In terms of manufacturing, they include a combination of forging, forming, joining techniques that can drastically reduce time through less inspections and commodity usage. Future manufacturing approaches will also benefit of higher levels of transparency and interconnectivity between manufacturing techniques. And finally, just highlight, and this is something that we will explore today, about it is important to create enabling conditions at the national level to accelerate the adoption of these construction and manufacturing techniques. There are initiatives like National Research Innovation Center in the US or Nuclear Advanced Manufacturing Research Center in UK that illustrate how it is possible really to identify low-hanging fruits, empower the industry, and at the same time facilitate the regulatory interactions. This is something we are going to explore today. So now, as I said, the objective today is taking a look into the future, focusing on additional constructability improvements that arise from smaller and more innovative designs concepts, such as SMRs. These designs have not only smaller components, but also enhanced safety features that invite to rethink the whole delivery process. At the same time, it is necessary to meet regulatory expectations and quality standards. So we will hear today from regulators, codes and standards, organizations and industry associations to create this environment to accelerate the adoption of the techniques. It is also a good opportunity to hear from other sectors, and I'm really pleased to have among our panelists, let's say, out-of-the-box thinkers, experts from shipbuilding industry, innovative design, construction companies to explore all of this. So as yesterday, we have two sessions with 4 or 5 presentations in between, and a panel discussion at the end of around 30 minutes. Also, since the agenda is tight, I encourage also these panelists to keep as much as possible the presentations between the allocated time. Let me also remind some housekeeping remarks. The chat function is enabled, but we are not going to monitor this. If you have any questions about the different presentations, you have the Q&A function enabled, and panelists are free to provide a written reply. And now I'm really pleased to introduce our keynote speaker. Her name is Mrs. Kirsty Gogan. Kirsty Gogan is the co-founder of and managing director of Zero Praxis. She's also global leader in the field of nuclear innovation, and she has more than 50 years experience as senior advisor to governments, industry, academia, networks, NGOs all around the world on climate change and energy policy. Kirsty is also the managing partner of international consultancy firm Lucid Catalyst and co-founded Energy for Humanity, an organization dedicated to advocating for clean energy solutions. So please, Kirsty, the floor is yours.
Thanks, Antonio. Thank you so much, everybody, and thank you for convening this webinar. I think it's very timely and important. So if you'd like to open my slides, thanks. I'm going to sort of talk about a kind of scale of ambition for how nuclear energy might really become the kind of new primary energy. I'll describe a little bit of detail how new near-term climate scale strategies can compete on price and performance with fossil fuels and help to break through some of the world's toughest, most difficult carbon emissions challenges, coal and liquid fuels. If you could go to the next slide, please. So this is why we want to focus on those sectors, coal and liquid fuels, because mainstream modeling consistently projects that most of our energy is still going to come from fossil fuels by 2050. And the hardest to abate sectors are listed here on the side: coal and gas and liquid fuels. And the reason that I'm showing this chart is because what we're actually looking at is a 3 to 4 degree trajectory of warming, and we have no plan to avoid that outcome. So if you could go to the next slide, please. Let's just look at coal for a moment, which boomed, of course, into record-breaking generation in 2020 and in 2021, despite all of our efforts, despite COP26. And in 2022, the world now has 2 terawatts of coal-fired electric power plants, adding around 12 gigatons of carbon emissions every year, which is around a third of our total global forecast annual emissions. Now, you'll have seen at COP26 and in the wider discourse that some policymakers, climate modelers, activists assume that countries are just going to shut down these plants and reduce emissions. But because most of the coal plants, in fact, around half of the coal plants in the world are actually less than 14 years old, it's really, we think, unrealistic to expect such young assets to simply retire. In fact, all of the evidence points to the contrary. And that's especially when you consider the growing energy demand and, of course, the supply shortages that we're all acutely aware of right now. And then even in countries with old coal, relatively old plants like in the United States and Canada and Europe, even there closing these coal plants is really difficult and controversial because the loss of jobs and revenues can be devastating for communities. And then, of course, the utilities also continue to value the reliable electricity that's generated. So the question is, if we can't assume that these plants will be prematurely closed before the end of their operating life, and assume that communities and societies are going to be willing to accept the economic harm that's caused by their closure, how can we repower all of the existing coal plant infrastructure in 28 years? And we go to the next slide, please. Because coal, of course, isn't the only huge challenge. This chart shows the very steep emissions reduction curve that's going to be needed and the shockingly short timescales within which we have to do that, not only replacing all of our fossil fuel infrastructure, but actually doubling or tripling it to meet rising global energy demand as well. If you could go to the next slide, please. Let's look at liquid fuels. So we use right now about 100 million barrels of oil per day. And our hypothesis is that the fastest way to eliminate those emissions is going to be to produce drop-in substitute fuels that can be stored, transported, and used in existing infrastructure, leveraging the existing global skills, capability, and infrastructure that's already operating at global scale. in the oil and gas and aviation and marine and industrial sectors. And if we're to do that, we're going to need a lot of hydrogen, and it's going to have to be very low cost, because hydrogen is the key ingredient for these drop-in fuels, ammonia and synthetic hydrocarbons. But if we're going to produce those synthetic fuels competitively to enable the drop-in substitute to happen, then the hydrogen is going to have to be very low cost. As you can see in this chart, the hydrogen will need to be produced at around less than $1.50 a kilogram, which is very ambitious for those of you following this. If you could go to the next slide, please. Now, I'm going to be focusing today on how nuclear technologies can contribute to these challenges, coal and liquid fuels in particular, targeting the toughest parts of the decarbonisation challenge. So keep this chart in mind. Okay, let's go to the next slide, please. So if we're going to have nuclear technologies contribute in this way, then we're going to need to design for the requirements, for the constraints. So the constraints that we're designing for here are cost and speed and scale and space. So let's look at these in turn. Next slide, please. So firstly, cost. I mean, there's a perception that nuclear is expensive. This is a chart from a study that we did for the Energy Technologies Institute a few years ago, and there's been excellent work done also by the OECD, NEA and others looking at recent experience in global nuclear construction. And the somewhat surprising finding is that the majority of plants being built around the world today are actually being delivered very competitively, as you can see, around the $4,000 a kilowatt mark. And the boxed out sample there in the top left of the chart is the first of a kind, first in a generation experience in the United States and Europe, where there's a small number of very understandable factors that led to those high cost outcomes, and are very addressable through programmatic approaches and through the application of some very well understood best practices, such as, for example, starting construction with a completed design. If you could go to the next slide, please. I'm going to show you a really good example now. So this is a chart showing the cost reduction trajectory over 4 units that were recently built at the Barakah nuclear plant in the UAE, arguably the world's most successful, first of a kind, first in country nuclear build. And they achieved this through some of these through the application of these best practices, such as using a finished design that had actually already been built multiple times, and importing the very experienced project management and work crew for those first 4 reactors that were then built on a single site in succession. So the average cost for the reactors ended up being much lower than the cost of the first of the 4 reactors. And you can see here that the cost between the first, second, third, and fourth reactors got progressively lower, with the fourth one having less than half of the capital cost of the first reactor. So the lesson here is that the surest way to make nuclear or anything really expensive is to do it once in a generation and then stop, and then dismantle all of the expertise and networks along the way each time. And the best way to bring the cost down is to do the opposite, lock in a design and then build it repeatedly. Next slide, please. So today we're going to hear about how we take some of those principles that I've just described for best practices and cost outcomes, and take them really to their logical conclusion, which is really moving from a project-based approach to a product-based approach, applying the absolute best in class design for manufacture and assembly, and moving into very high productivity manufacturing and delivery environments. This is a very important way of also shortening the construction schedule. You could go to the next slide, please. So that was cost. So let's look at scale. So we need to start thinking about the scale of the challenge that we're actually addressing. And this is really a big shift in mindset for the nuclear sector, which only has around 400 gigawatts of plants operating today. So if we're pointing nuclear technology at the fuels challenge, for example, we're going to need a radical shift in perspective and ambition. So we use today 100 million barrels of oil, equivalent to around 15 terawatts of energy use. That's around 14,000 fuels production platforms if we were to deploy offshore shipyard manufactured fuels production platforms that you'll hear about later in the presentations today, to replace all of that use. 14,000 sounds like a lot, there's 60,000 large ships already operating in the world today. So it's also important to look at the scale in the context of what's already happening elsewhere in other sectors. Next slide, please. Now, those large ships, they operate for about 20 years, and then they need to be replaced. So world-class shipyards are actually already producing more than 1,000 ships globally, and these shipyards themselves are even operating at around 50% of their potential capacity. So you can see from this chart that global shipyards could actually achieve that very ambitious scale and rate of deployment that would be needed to produce those 14,000 platforms. Go to the next slide, please. Now, I think we may have skipped a slide. So scale also is important in terms of thinking about the scale of capital investment that's going to be needed to achieve the global energy transition. Oh no, it's okay, you can go back, thank you. Right now, the global oil and gas industry is projecting around about a $24 trillion investment over the course of the next 3 decades to 2050 to maintain the current supply of oil and gas, which is what's projected, by the way, in that chart that I keep coming back to each time. So, you know, that's capital that's already sort of earmarked, if you like, for investment. If we were to try to replace that oil and gas flow with hydrogen produced by renewables, you can see on the right-hand side there that would require a radical increase, a tripling almost of capital investment. Now that's in the context of the need for a huge investment, unprecedented investment at a rate that we've never seen before to continue the larger decarbonisation efforts needed globally and investment in additional infrastructure as well. So thinking about ways of reducing that capital is also going to be very important. And that's what our conclusion is if we were to use nuclear technologies because of the particular attributes of high temperature heat, which produces very high efficiencies, very high productivity, combined with very high capacity factors, tiny environmental footprints, and potentially very low costs and delivery with these high productivity manufacturing approaches, we could actually lower the overall cost of producing the energy required. My 11-year-old, when I told him about this over lunch one day, he said, wait, so you mean it would be cheaper to save the world than to destroy it? It's a funny perspective. Next slide, please. And then, okay, speed, right? Our next big requirement, right? So it is tempting to think that nuclear is very slow and too slow to make a meaningful contribution. And the interesting thing is that it's already making even the traditional approaches to construction, even some of the not great examples of our nuclear construction are actually delivering, you know, a very rapid transitions for their societies. The thing is that nuclear plants are big, and for that reason, they take a long time to build, especially given, you know, the regulatory environment that they're operating in. And you can see that, you know, the delays that have been caused at Flamanville, Olkiluoto, and Vogtle, and so on, they're explainable, as we've just discussed previously. They're first-of-a-kind projects, starting construction without a completed design. But actually, the global average construction time of nuclear plants is around 7 years, and the fastest ever large nuclear new build reactor was in Japan, which took about 5 years. No, actually took just over 3 years. But even the sort of failed construction projects aren't that slow. And you can see that in the graph here, that even Olkiluoto, for example, in Finland, as a single project, which took 16 years from start to finish, has actually been faster on a per capita basis than wind and solar combined in any nation at any within any time, the same time frame. So while it takes a lot of years to build a nuclear reactor from start to finish, the payoff is enormous and worth the wait. Now, obviously, we should build wind and solar, and these technologies are maturing and their installations are getting faster and their costs are getting lower. They're faster to set up. But if a single facility is 1,000 times smaller than a large nuclear reactor, 1,000 times more facilities need to be built to get the same energy output. So really, we ought to be doing both. Okay, if you could go to the next slide, please. So finally, space. So we've heard about cost and speed and scale, and now let's look at space. So you can see here a map showing the space requirements, the area required if you were to replace the UK's current oil consumption with hydrogen generated either from wind or solar or advanced heat sources. Wind is in the big pink, which is sort of projected to be a kind of continuous wind farm filling the entire area, which isn't actually feasible, but this is just a thought experiment to give us an idea. And if you could go to the next slide, please. We have a similar map for Japan. Now, the major oil companies that we're working with are really acknowledging this critical constraint to their ambitions to replace their fuels production with green hydrogen produced from renewables. It's really becoming apparent that actually the scale of production that's going to be viable with these technologies just isn't going to be able to match the kinds of scale of production that the oil and gas sectors are being able to achieve today. Next slide, please. Those are the design requirements: cost and speed and scale and space. Now let's look at how we meet those through some innovative design approaches. If you could go to the next slide, please. So you recall the critical sectors that we need to target, and now we're going to look at some deployment models that can address them. We could go to the next slide, please. So you'll hear today about two new approaches to meet the challenges presented by coal and liquid fuels that are being designed to meet these climate scale and time scale requirements. So firstly, repowering coal. This is a program of work that Eric Ingersoll will be presenting on shortly. The vision is around the opportunity to repower our global existing coal plant infrastructure in a way that can greatly accelerate the clean energy transition and also enable a just transition. And if you could go to the next slide, please. Liquid fuels, you see here a refinery scale hydrogen gigafactory, which has around 36 high temperature heat sources equivalent to around 20 gigawatts installation. Because this facility is producing commodities rather than electricity, it's possible to achieve a scale of installation which enables the full integration of the manufacturing, installation and production facilities all on one site. 20 gigawatts sounds like quite big to the nuclear industry, but actually it's equivalent to a small refinery. So again, it's important to match the scale of the sectors that we're addressing, and also to put the scale into the context of the scale that we're addressing, of the markets that we're addressing. This facility would produce hydrogen at less than $1 a kilogram, and 10 of those would entirely replace the UK's current oil consumption. Next slide, please. And then you'll hear, I think Andrew Sauder is going to present a new study about shipyard manufactured fuels production platforms. The idea really is that either you bring your factory to the project, which is the gigafactory that you just saw, or you bring your project to the factory. And in this case, we'll be looking at world-class shipyards, which are some of the highest productivity manufacturing environments in the world. Next slide, please. So in conclusion, we've talked about cost and speed and scale and space, but really it's all about cost. Let's get next slide, please. Ultimately, we need to like move way down the pathway to low cost here. You can see the first of a kind bar is the kind of benchmark set by some of our recent experiences in Europe and the United States, but how quickly you can radically reduce that down to a $4,000 a kilowatt level just through programmatic learning. But it's possible to go much further, and that's what we will be hearing about through the rest of the presentations in the session today. So thank you so much. Back to you, Antonio.
Perfect. Thanks a lot, Kirsty, for sharing really this vision, which is going to shape the discussions today. It's important to have an idea of the importance of scale, cost, and speed in order to meet climate targets, hard-to-abate sectors, but also interesting vision to leverage the existing infrastructure. So with this now, the idea is how this vision could become a reality, and now we are trying to explore this in the next session, which is called Improving Constructability with Small, Modular and Innovative Nuclear Designs. It will be moderated by Mr. Chirayu Batra. Mr. Batra is nuclear engineer and project officer working on advanced reactor technologies at the International Atomic Energy Agency in Vienna. He's responsible for planning, organizing and implementing IAEA's activities and projects in the field of SMRs and their applications, including coupling with renewables and non-electric applications. He has experience in advanced reactor modeling and simulations, and also coordinates several international benchmark studies on modeling and simulations, and manages the IAEA's initiative on open source nuclear codes for reactor analysis called OnCore. So please, Chirayu, go ahead.
Thank you, Antonio. Thank you very much. Hello, everybody, and welcome to this workshop's third session on improving constructability with small, modular, and innovative nuclear designs. Please allow me briefly to describe what we wish to achieve through this session. I'm having some troubles in starting my video. Give me a second. Okay, I think it's on now. Antonio, it's okay?
Perfect.
Modularization, as you know, is the key concept when we talk about SMRs. And the SMRs could be modular in design, construction, or in the number of modules that are installed. It is therefore very important to understand advancements as well as innovation in the area that can actually make SMRs cost competitive as well as mass deployed. As the whole workshop invites discussion and deliberation on advanced construction and manufacturing methodologies, specifically for nuclear new builds, we will try in this session to analyze potential constructability enhancements associated with small, modular, and innovative nuclear designs. The shipbuilding and aviation sectors are often regarded as successful delivery models that could potentially be explored with small modular reactors. More innovative and design approaches could lead to significant design simplifications and reclassification of safety-related components, further improving the constructability. But the question arises that what can we essentially learn from other industries? What experience can be adopted? What new approaches might be needed? And how can we actually practically do this? There are several other questions that arise when we talk about new ideas or approaches, and more so when we talk about them in the nuclear industry. Therefore, I, along with our distinguished panelists, will try to explore these together. And I also invite all of the attendees to get fully engaged and keep asking questions through the sessions, throughout the session. And what I will do is I'll try to take some of the questions in the Q&A session, though we also have a design panel session. But I hope we'll get some interesting questions from you as well, and I will try to take them and ask our distinguished panelists. So therefore, without taking further time, allow me to introduce our speakers for the session. We have today 4 distinguished speakers with us who will give a brief 10 to 12-minute talk each. Unfortunately, due to unforeseen circumstances, Mr. Hervé Glandes, our 5th speaker, is not able to join us today. Mr. Hervé Glandes, Senior Vice President in Barracuda program at the Naval Group, was also supposed to be here with us today to talk about the modularization strategies for construction of submarines. Unfortunately, we'll not be able to hear his talk today. However, we have with us Professor Locatelli. He's a full professor of complex project business at Politecnico di Milano School of Management. His research is about project management of complex infrastructure. He focuses on benchmarking, cost-benefit analysis, risk management, decommissioning, ethics, and dark side. Okay, welcome to the dark side. Governance, financing, modernization, and value management. He also works as a consultant and visiting academic for several public and private organizations. He has authored more than 100 international peer-reviewed publications. Our second speaker, Mr. Sauder, is a senior technical executive at the Electric Power Research Institute, IPRI. He provides strategic support for the Advanced Nuclear Technology Program and nuclear sector, including government project development and engagement with the fusion energy technology community. He established IPRI's Advanced Reactor Strategic Focus Area and previously managed applied research on advanced nuclear fuel cycles and used nuclear fuel management. Our third speaker, Mr. Jamie Johnston, MBE, is board director and head of global system at Bride & Wood. He is a leading authority on industrialized construction and design for manufacture and assembly, and works on new data-led digital workflows for government and private sector clients in the UK, US, Europe, and Asia. And finally, our fourth speaker, Mr. Eric Ingersoll, co-founder and director of TerraPrexis and a managing director at Lucid Catalyst, is a strategic advisor and entrepreneur with deep experience in the commercialization of new energy technologies. He has extensive project and policy experience in renewable energy storage, oil and gas, and nuclear, with a special emphasis on advanced nuclear technologies. Eric develops commercialization and market entry strategies for advanced energy technologies, such as advanced nuclear power generation, carbon capture, and zero carbon liquid fuels. Thank you all for joining us today. Now, without taking too much time, because we are already a little bit delayed on the schedule, I invite Giorgio to kindly make his presentation on techno-economic analysis on modularization and complex project management. Giorgio, the floor is yours.
Thank you very much, Mr. Chairman. Thank you very much, Antonio, for the invitation to this meeting. I'm very pleased to be here today. My presentation is about the techno-economic analysis of modularization and complex project management. Next slide, please. So when we open our newspaper, we are always flooded with information about a nuclear program, nuclear project that are over budget and late. This is a major concern for finance. The first thing that we need to keep in mind is that these headlines are mostly in Europe and the United States. When we go to the Far East, the situation is radically different. Next slide. Also, this is not in news, again, in country like the United States, where the cost overrun of a nuclear power plant was already there during the 60s and the 70s. This is a report from the Congressional Budget Office made in 1986 that shows the average over budget for the nuclear reactor in the United States was 300%. A key point to remember is that this doesn't mean that those are bad projects. This simply means that the final cost was 3 times as much the budget cost. And maybe there was nothing wrong with the project either. The cost was higher because the budget cost was far too optimistic. So when we look at in this, we need to recognize the problem of delivering something that is 3 times cost overrun, but we also need to remember that the fair analysis should be the final cost versus the final benefit, which is not captured by this kind of tables. Next slide, please. And yes, we can have a nuclear power plant on time and on budget. So if you go to the International Atomic Energy Agency, you can download website, it's publicly available, and you can download the construction time of all nuclear reactors in the world. Okay, it's there. And that's a very good indicator because while costs are always arbitrary because depend what you include, what you exclude, there is inflation, there are exchange rate, construction time is a pretty straightforward indicator between first concrete and commercial operation. So I did that for the standard 1 gigawatt Korean PWR. And what I saw is that in South Korea, they are able to constantly deliver power plant, nuclear power plant on time, on budget, and with a time that is between 4.5 and 5.5 years. These make nuclear power plant extremely competitive. These make nuclear power plant financeable. So there is nothing wrong with the technology, because this is the same technology that was a 3 times cost overrun in the United States. It's the standard PWR of 1 gigawatt. What it is about how you manage project, or even better, how you manage a program. Next slide, please. So if you go to the literature, and I'm a professor of project management, so I'm supposed to read a lot of paper, you find that there are database of large project and large energy project. Here I'm recommending 4 excellent papers to look at that. And the bottom line of this paper is that when you go big, you are more likely to be on cost overrun. So 90% of the project in the world suffer cost overrun. And there is a strong statistical correlation between cost overrun and size. This is not just in nuclear, or in all kinds of infrastructure. Larger the project, more likely you will be over budget, and the over budget will be greater in absolute and relative terms. This is what tons of research made by very different people show us. And ideally, when the project is bigger, become fragile. So when you have a large project and things start to go wrong, they are very, very hard to fix. And this apply to, is correlated to the size of the project. Why? Because maybe you have very few suppliers that you can switch to. There are very specialized equipment. You have cranes that are like so big that you have just one or two in the continent, and so far and so forth. So there is this idea that larger the project, not only you are likely to be over budget, the project become fragile. Next slide, please. So I believe that this comes from a big misunderstanding about economy of scale. So traditionally, we think about economy of scale as the idea that when you increase the size, the unitary cost decreases. And that's true, absolutely true. However, after a while, you become too big, let me say, and you encounter what we call diseconomy of scale. So you're building these white elephants that are unique, are fragile, and are full of risk. And all the stakeholders have the wrong incentives. Because if I have to deliver just one project, I have all the incentive to take advantage of you. If I have to deliver 10 projects, I know that if I am poor in delivering the first project, you are not to buy the other 9 from me. Next slide. So what we know that it works is what we call economy of multiples. The idea that the cost decrease according to the number of units that you produce. And this is everywhere. So look at your computer, look at your mobile phone. These are so cheap because we make millions of them. This is true for renewable, as we saw that the cost was decreasing in the last 20 years. And this is very true for instance, another sector that is safety-based, that is the aircraft industry, where Boeing or Airbus produce a new type of aircraft. They don't do 20, they do 200, 300 at least of those aircraft. Next, please. So I think that we needed to think a bit more about this idea. So traditionally, we have a monolithic plant that we break down in sub-elements. We call this modularization. But at the end, we still have one plant. At the end, when the plant is built, there is no difference. And then we have standardization, what the Korean did. The idea that you rebuild this plant over and over and over. What my research shows is that the real advantage comes from modularity. When you bring together modularization and standardization, this is what the aircraft industry does, because aircraft are both modular and standardized. So they really achieve modularity and they achieve low cost. Same for the wind industry, same for the solar industry, same for the computer that is in your desk now. Next slide, please. So standardization comes in two forms. Standardization comes as physical standardization. You are delivering the same product or the same service all across different markets. Coca-Cola is the same everywhere, despite they change the font according to the local alphabet. If you look at Ryanair, that's one of the most interesting cases. They have 300 aircraft that is always the same aircraft. So one is physical standardization, and the nuclear industry is starting to learn this. The second one is the project delivery chain standardization. So not just the supply chain, the project delivery chain. This includes the standardization of the contractor, but also the owner, the sponsor, the safety agency, and so far and so forth. So all the stakeholders involved in the project. This builds long-term trust, build long-term value, and increase the capabilities, that is a key element of the stakeholder involvement. Next slide, please. So what about risk? Yes, when we go toward the modularity, so when we go to small modular reactor, there are first of a kind costs that are unknown. This is true for large and small. But with a small reactor, you are, let me say, gambling far less money. Instead of gambling 10 billion, so putting 10 billion at risk, so you need to finance 10 billion that are very, very expensive, you only to finance 2. There are exogenous risk. Exchange rate, interest escalation, legislation change. Yes, they are true for large and small, but small are faster. There are endogenous risks. So if you look at a power plant like in Flamanville, and this is public information, you see there was a lot of rework and design mistakes, for instance, for the weldings. And you can do mistake on large and small, but on small one, the mistakes are usually easy to correct. And second, again, you are playing around with 2 billion and not 10 billion. So it's much easier, it's much better to learn on a small scale than a large scale. Similar apply to the mistake of supplier and the worker in the site. Next slide, please. So this is probably the most important slide in my presentation. So when you have one standalone reactor, you cannot do benchmarking. So you don't know how much it's going to cost. You don't know what are the risks. One of the most important things when you have a complex project is that you start from a completed design. So many times we have nuclear reactor in the UK and the USA that started without a completed design with tons of issue. And you have that when you have a standalone reactor. You are not having that when you replicate reactor. You develop stakeholder accountability. Yes, of course, because if I have to sell you just one reactor, well, I can tell you all kinds of misleading messages. And once we started, you have to continue. You have to continue. When you are 2-3 billion in the investment, you're not going to give up. When you have modularity, you can do that because after the first units, you can say, stop, thank you. You can have economy of multiples, the idea that you have learning from the stakeholder involved, and you can exploit siting economy. And lastly, there is the point of the economy of scale. You don't have to be too small or too big. And this is country dependent because each country is different. Each country has its own needs in terms of electricity. Next. That's it. This is the idea that I wanted to share with you.
Oh, thank you, Giorgio, very much. It was, I think, a very interesting presentation, giving several key insights, including concepts like modularization, standardization, how they interact, how both of these are important in a project, the stakeholder accountability, including how can we also learn from different stakeholders who are involved in that and how accountable they should be, and what to do about economy of scale. I think that was an interesting part where you said how big is actually too big. So this needs to be also understand at what point the economy of scales actually starts to become more complex project than being cost effective. Okay, so let's move to the next speaker, Andrew. He will present today on rethinking nuclear deployment for zero carbon energy at scale, a vision for 2050. Andrew, the floor is yours.
Okay, well, thank you very much, and I appreciate the opportunity to share some of the work EPRI has done. Appreciate the invitation from the NEA to share today. So, along the lines of what we heard initially from Gogan and then the first speaker, I'm going to actually focus on what EPRI has done in terms of visioneering for the future, on how to rethink nuclear deployment. Next slide. So what I'm going to do in the time I have today is summarize a study that was recently published in December of last year, and it's publicly available, so the URL is there at the bottom. And as the title says, this was a study intended to rethink how we go about deployment of new advanced reactors, scale and time frame of decarbonization. I will admit, though, that when we first started this project, we were probably asking the wrong questions, because the study initially began looking at what was the market potential globally for nuclear power in non-electric markets, with an eye towards decarbonization. Well, again, the problem is, starting from that direction, we were essentially asking the wrong question because we were chasing after the markets using the current deployment model. And what you ended up having is a very fragmented approach, but facing all the same construction issues. Next slide. So with the help of Lucid Catalyst, who worked with us on this study, we refocused when we realized actually the most important aspect of making nuclear or allowing nuclear to have a role in decarbonization and meeting future energy needs, really one that Kirsty emphasized at the beginning, which is establishing a scalable model, but also one that can deliver on time frames that matter. So what I'm sharing here are the key study tenets that we settled on. And again, I will be the first to admit we did not start out asking or looking for a shipyard model. What we started out by asking was, how do you get nuclear to play a role, a significant role, in supporting decarbonization by the year 2050 on a global scale? And what came out of that was, in fact, 3 of 4 scenarios that were indeed focused on fabricating the entire standard plant and its platform in a fully engineered environment. And as it turns out, that environment is, in fact, available in the form of large modern shipyards. So essentially, what you are doing is you're replacing the land-based site and all the challenges that go along with it with the ship, the platform itself. Once you have the ship manufactured, then you can deliver the plant to the point of use via marine conveyance. In other words, then deliver the plant itself to where you need it, rather than vice versa, having to build the plant at the site itself. Then the next tenet or fundamental principle of the study was one of the best ways to actually decarbonize, hard to decarbonize sectors like heavy-duty transportation was through the production of storable, conveyable, and as close to drop-in substitutes for fossil fuels that are used today. This also allowed us to then take advantage of another important model, which is the floating production, storage, and offloading, or FPSO model, that the oil and gas industry already is using around the world today. And then finally, being able to then utilize these models to supply zero-carbon synthetic fuels and products to the market at competitive prices. I will just start off by saying the study itself is technology agnostic with regard to the nuclear power source. We're focused more on the deployment model itself. However, we did focus on high-temperature reactors, high-temperature heat sources, and we ended up utilizing a specific design, and a developer shared with us actual price or cost estimates from a number of credible suppliers. And that was a liquid-fueled molten salt reactor. Next slide. So the question then becomes, is in fact moving to a shipyard-based deployment of zero-carbon fuels feasible? And so here I've just included all of actual photos to convey what we saw as evidence that this is indeed practical, if as yet not yet demonstrated. So starting from the top left and moving counterclockwise, on the upper left, we see the Samsung shipyards in Korea. Again, these exist today, and as Kirsty had mentioned, these shipyards are capable of producing some of the world's largest structures, multiples every year. Moving down counterclockwise to the lower left, you see one of Maersk's large container ships under construction, and this again illustrates the modular fabrication methods taken to the extreme, where each block is put into place and essentially already outfitted and fully assembled and ready for mating up to its neighbor. Moving now over towards the right, what I'm showing here is the Petronas Dua. This is in fact one of the newest of FPSO ships. This is being shown in the same South Korean shipyard as it's being outfitted. So what you see on top on the deck of the ship is in fact a floating equivalent of a floating refinery, capable of producing and does produce refined products at sea and store them until offloaded for distribution. And then over on the lower right-hand side, we are getting into the nuclear portion of the evidence, which is, I think most people are aware that Russia deployed the academic Lomosov as a floating nuclear power station for production of civilian combined heat and power in its territory. And then finally, the origins of nuclear actually lie in ship-based naval propulsion. Again, the first nuclear applications were to power submarines and surface ships. So together, individually, these elements suggest that combining all these together could indeed and should be feasible. However, of course, devil is in the details, and this a true commercial application of this is yet to be deployed and demonstrated. But again, a number of developers are in discussions, and you have seen talk about nuclearization of both shipping, commercial shipping, as well as production of electricity, as well as zero carbon products. Next slide. So this is really what I wanted to focus on, is what is the significance of moving to a shipyard-based construction? And really the significance lies in the fact of controlling, maintaining cost, schedule, risk, and uncertainty. Because essentially what you're doing with a shipyard and a ship-based nuclear production model is you're replacing the land, the site, and many of the and much of the all of the civil construction with a fully engineered, controlled environment that's already demonstrated and in use. So these numbers I'm showing here aren't exact, but it's essentially kind of a thought experiment to illustrate how in fact you do achieve these savings. And so on the left is a common reference cost breakdown for a gigawatt class large light water reactor. And as you can see, the actual equipment and direct construction costs are just a third of the overall cost of the project. It's often said that the vendors could give away the nuclear plant and balance the plant away for free, and the project would still be too expensive. So in theory, by moving to a shipyard or other engineered environment such as the gigafactory that Kirsty illustrated, much of those or all of those lower costs associated with one-off stick-built plants located on land, which involves enormous amount of earth moving and civil works, those costs essentially disappear. Of the remaining costs, financing during construction and then the actual direct construction costs of equipment, labor, and materials, with the shorter construction duration and more predictable, this is just an estimate, but the financing costs should go down at least in half, if not more. And of course, with the controlled environment and the skilled labor there, trained and repetitive work and automation, again, those direct construction costs could indeed come down as well. So with this, just a thought experiment, essentially you come up with a reduction in costs below $2,000 per kilowatt electric, which is essentially consistent with some of the best, actual best plants already deployed globally. So the number itself isn't unrealistic. Next slide. So at the end, what matters are the economics. So again, I mentioned that we looked at 4 scenarios. Again, I did not spend time today on these scenarios themselves, but rather the deployment models that make them possible. And we did indeed use traceable technoeconomics, including the nuclear estimates were from an actual developer and from estimates provided by a competent shipyard in Asia. So these numbers were indeed probably as close as you can get today to a high confidence number without actually building a plant. What we found was indeed the numbers, the cost of the zero carbon fuels, for example, for Jet A, complete drop in fuel substitute for jet fuel is indeed competitive with the current, well, the benchmark price circa 2019. Ammonia for shipping, a like-for-like liquid fuel for liquid fuel replacement of bunker oil and diesel, again, close to current global prices, but again, zero carbon footprint. Hydrogen, as Kirsty mentioned, just below $1 per kilogram, and electricity at a very competitive price, as well as desalinated water. So I would encourage you to take a look at the report. I believe it has been posted online, and it's also available by visiting EPRI.com, as well as at the beginning of the talk for more details on how we came up with these numbers. But the conclusion is scalability and the new look at the deployment model is really one that enables the scale needed for nuclear to really compete and to make the difference needed for meeting both decarbonization goals, but perhaps more importantly, continued reliable energy and electricity needs. So that's it. Thank you.
Okay, thank you, Andrew, very much again for this insights. And I think you did a good job in reiterating that what matters is economics, as Kirsty said as well. So I think we have to, in the nuclear industry, I think economics of cost is always something that we have to answer or maybe rethink. And as you said also, other than a lot of things that we need to rethink, I think rethinking the deployment strategy is definitely one of them. I've read the report that you mentioned, and I think it's quite interesting. And I also encourage the attendees to take a look at that report. I have also noticed that this scenario or this approach of changing the land-based site to shipyard-based site is already being adopted by a few SMR startups. And I hope they will try to follow this through and see how the outcomes are by following that strategy. What I also believe is that having a very solid delivery model and innovation in manufacturing will be very important in such kind of transformation, and it could become very important. But thank you again, Andrew, for this great presentation. Okay, let me now invite Jamie to talk about some interesting examples from the UK government's platform approach to industrialized construction. And I want our next speakers to be kindly aware of the time constraint that we have. I don't want to rush you in. Please take your time, but let's keep a little bit time in mind as well. Thank you. Jamie, please go ahead.
Thank you. I've started the stopwatch, so I'll try and.
No, not on time yet.
Firstly, can you see my screen? I'm sharing my slides. Can you see that?
Yeah, I can see it. It's in full screen. Please go ahead.
Perfect. Okay, thanks a lot. Yes, as you heard in the introduction, I've spent my career working in public and private sector, trying to help people transform construction from the sort of current labour-intensive, carbon-intensive, low productivity industry we have into something more like manufacturing, with all the benefits that manufacturing's seen in terms of safety, quality, productivity, etc., etc. So that's been quite a long journey. A lot of my time has been working with UK government, so trying to get a client with a long pipeline of projects is one of the ways that we're really going to sort of shift the needle on this, and that'll echo with some of the things you've heard from other speakers. So despite the topic of my talk, there's nothing I'm going to talk about in this approach which is actually UK specific or centric. So this is a response to global challenges, and so if the solutions we're looking at are of any use, they've potentially got massive global applicability. And while I'm going to talk about sort of approaches to buildings and roads and things, which is obviously what UK government's spending money on, there's nothing in this approach which is specific to those sectors. And actually, Eric's going to talk after me about the application of this sort of thinking to the energy sector. And hopefully you'll see parallels actually with things that I'm going to talk about and what the previous speakers have mentioned. So these are some of the common challenges that every client in any sector seems to be facing at the moment. So I won't read them all out, but you can hopefully see these are not kind of specific to construction of buildings. These are the things that everyone's facing around sustainability, productivity, technological advances and things. And so how do we start to respond to those, and how do we start to fundamentally change the things we do? So UK government has been on a journey over at least a decade now, but certainly over the last 5 years, it's been persistently shaping its strategy to how to use its pipeline and its spending power to transform construction. You can see some of the wording from the autumn statement. We're going to use this lever that we have to change construction. And they arrived, I think, at the same conclusion that the earlier speakers have mentioned. So I didn't know what Giorgio was going to talk about, for instance, but or Kirsty, but one of the things they've recognized is that this treating every project as a bespoke one-off, never capturing the learning, never transforming things in that way, is one of the things that's massively holding us back. And looking at the differences between sectors is one of the things that's kind of blinding people to some of the solutions. So you'll see as we move on to the right-hand side that some of the language they've started to use is saying, we're going to look for commonality across sectors. We're going to start to use common components. We're going to start to use repeatable designs that I can use again and again, refine over time. And that's how I'm going to get into the sort of continual improvement cycle that manufacturing does so well. So one of the key themes or concepts they developed was this idea of saying, rather than focus on the difference between every sector, so rather than think of education and healthcare and prisons and et cetera, et cetera. So if you looked for commonality between lots of building types, almost certainly you'd find there's loads of commonality. So things like, building floor to floor heights are set by the size of people, for instance, which means you can get light 8 meters into a building. And that's why schools and apartments and healthcare all have the same sort of spans. So one of the key themes was saying, how can we get more granular? And I think it's like Giorgio's slide where it showed the kind of modularity. How do I identify those components that we could configure in lots of different ways across lots of different sectors? That's how we'd get into the sorts of numbers that manufacturing likes. And that's how you start to get the economies of scale. One of the precedents we used with government was IKEA, because everyone's actually already familiar with this sort of platform concept. So one of the things IKEA did, they weren't the first to do it, but they're certainly the ones that have done it at greater scale, was take furniture making, which was a very skills-based, trade-based, labor-intensive sort of bespoke process, and boil that down into a tiny handful of components that you'll all have used at some point making IKEA furniture, and still get a range of furniture. So, but that whether you buy a wardrobe or a bed or a chest of drawers or a bookshelf, the components are always the same. But on Giorgio's point about the supply chain, actually the process is always the same, the book is always the same, the tools are always the same. So they've turned what was a kind of quite bespoke process into a very small series of repeatable components, repeatable tasks, small number of tools. And actually the supply chain for furniture manufacture is now everyone in the world who's made a piece of IKEA furniture. So that was the sort of thinking of saying, what does that look like for construction? And we've made some big strides in this in the UK. We've developed lots of these solutions. I don't have time to talk about them in detail, but I'll show one example of it in a couple of slides. The reason the government wants to do that is because if I had that repeatability, suddenly I get into a kind of stable pipeline or demand for the same components again and again. Suddenly I get kind of stability in the supply chain, that if they know there's this consistency, they can gear up and meet me halfway. Suddenly my components become more fungible, so I can buy them from any one of a number of suppliers. So my supply chain becomes more distributed and resilient. And suddenly I get to leverage all of the things that manufacturers do. So one of the sort of themes was, if you had standardized components used at scale, you could automate the design process because every component could be taught how it relates to the others. You could automate the delivery process because you could start to manufacture things with robotics. You could suddenly start to increase productivity because you'd sort of boil construction down into repeatable, safe tasks and sort of do the thing that manufacturing's done. So automotive, for instance, doesn't use mechanics and engineers to build cars anymore. It uses people who were trained to assemble components to make cars. And we've seen in the UK already, we've been using this to take ex-army people to build pharmaceutical facilities. We've used prison industries, we've used unemployed people. So you suddenly diversify the workforce, you create new jobs and opportunities, and you start to transform this sort of whole industry into something that's much more like manufacturing industry. So I'm going to show a video which hopefully will play, which is, it's one example. It's one of the kits or parts we've developed being used to build a superstructure. But what it demonstrates is that with a very small number of people, with a very small number of components, we can actually build a superstructure of a building that ordinarily would take an army of people, a team of people building things very slowly. So this was the prototype, but we've actually done this live on site now. So what you're seeing here is the building of a 9 by 9 meter grid for a commercial office. But what you can see is there's a very small number of people on site. We're measuring activities in minutes, not hours. The components are very straightforward to assemble, which means the skills are very low. This team is actually working they're building the floor above from the floor below, so they're never working at height. So they're always working very safely. The components are laser cut, so they go together very precisely. There's a little bit of automation. We're using very low carbon materials. So this has demonstrated on a live site, this project is the first, for instance, net zero carbon building in the UK or commercial building in the UK. And we've demonstrated you can almost certainly build most building types about twice as quickly with about half as many people. So a 4 times increase in productivity, which if you then apply that at the scale of UK government spend, we're going to start getting some quite dramatic impact in terms of cost and carbon and productivity and things. But you can see here a lot of this thinking chimes incredibly well with what the previous speakers have talked about in terms of, commonality, repeatability, consistency. This is how we're going to start to shift the needle. The other part of that is, so one aspect of that is kind of physically building things we can be much quicker and much safer. The other part is if we're using digital libraries of those components and each component knows how it relates to the other components, then you can start to automate the way those components go together. So we've been developing a whole range of computational design workflows, algorithmic workflows, automated workflows that mean that rather than a designer sort of slowly developing 1 or 2 concepts, we can use an algorithm to generate 100,000, 1 million totally compliant designs. So it can't ever design a thing which is not compliant, can't ever break the rules. But it means that rather than sort of do a linear normal design process, try a couple of ideas, you actually test millions of ideas and then down select and say, well, show me the ones that have the least amount of cut and fill, the best utilities, the best site utilization. So it's a much quicker, much better design process. You test more ideas, and you can imagine, I'm sure this will be relevant to nuclear, you can approve the components, the processes. You can write all of the kind of approvals things into the code, which makes your approval process much quicker because you can only ever generate a compliant design. So we've developed lots of these, again, in public and private sector across lots of different sectors. The one I'll show you a video of in a second is the thing called Rapid Engineering Model for Highways England. So we worked with Highways England to take all of their technical design standards. We codified those. We had a library of all of the components they use for motorways, so all the gantries, the refuge areas, the signage, all those sorts of things. We generated a algorithmic assessment which takes a section of the country or a section of road, analyzes that, and then it auto-populates that model. So it knows what sort of context every component is looking for. It knows the visibility distances, it knows the gradients, it knows the curvature of the road, and it automatically generates a quite advanced now design But to give you a sense of the speed of this, it now generates the same quality or a better quality design in about 2 days, maybe 4 days, that it used to take a team of 25 people 15 months to generate. So the speed with which we're generating things is not 50%, 6% quicker. It's in a fraction of the time. So again, if you think of the sorts of numbers that Kirsty was talking about earlier that we need to populate these things at, you can't design those scheme by scheme. The only way we think we're going to get to some of the numbers that Kirsty talked about is by using very repeatable manufactured components at scale, driven through automated design processes and approvals. So this video gives you a sense of how rapid engineering model works. So it takes a stretch of motorway, it automatically assesses it, looking at curvature and gradient and all of these features. So it builds a kind of mental picture of what the road is like. It then, because every component knows how it relates to the road and each other, automatically generates the design for you. It can never break the rules. It actually finds better solutions than humans do because it tests more things and tries more concepts. It will also now look at ecological, visual and heritage. So it will design around constraints within the site, and then it instantly generates lots of different ways of interpreting or engaging with the model. So it creates sort of a geometry version, it creates a data set, it generates a model where you can be a driver of a truck or a CCTV camera, and it does all of this kind of instantaneously almost. So the speed, as I say, is like 4 days. So all of this model was completely generated, automatically. No human was engaged in this, and potentially now you could run it on the entire UK road network and make the network better. But it's certainly being deployed at scale by Highways Agency. And then there's another version of this which is evolved for Network Rail. There's another version of this which is evolved for Transport for London. So what we're seeing is more and more industries taking this and propagating it across sectors. And we're seeing more and more people taking the kind of component approach. So I think there's a massive overlap, I'm sure you can see now, between the sorts of approach UK government's taking it, and they've arrived at exactly the same conclusion as most of the speakers today. So I'm going to hand over to Eric now, who's going to show you an application of this in the energy sector. So
thank you very much. Yeah, thank you very much, Jamie. I think if I take some key insights from a presentation listing the common challenges which I think every industry deals with, and more so in a regulated industry like nuclear, we have to think more about it. Then treating every project as bespoke, one-off might not work for our industry as well. And this has also been iterated by the previous speakers. I believe that EKI is a valued case study for all industry. Maybe sooner or later, we will also get into the era of 3D printed reactor components, and there we'll see how we can also make this assembled models in future. The highlight was when you said that we should design in a way that you can't ever break the rule. So I think this is something that if we can do in the nuclear industry, following all the codes and standards, not breaking a rule, that will be the highlight of achievement for our industry. And I'm also eager to see and know how many configurators is nuclear industry using or willing to use in future. I think it was very insightful to look into what other industries are doing and what nuclear can learn from that. And then now taking some of those learnings, we will now see what Eric has to present in terms of how nuclear industry can actually adapt some of these approaches and tackle some of these challenges in this regulatory industry. So he will be presenting on a platform for repurposing coal. Eric, the floor is yours.
Thanks, and thanks to all the excellent presentations before. I think you'll see this is really like a case study to apply the kind of lessons and best practices and guidance that the previous speakers have shared with us. So we said, what if, building on what Kirsty was saying in the keynote, what if we really had to repower 2 terawatts of coal? What if we were living on a planet where we were threatened by really serious climate change and we had a short time to deal with it? And we didn't have time for political fights with people who own coal plants and stuff. We just have to convert all of the infrastructure to clean infrastructure as quickly as possible. So we had been doing a lot of work on open architecture nuclear systems and how to build a horizontal delivery model for the nuclear industry. And that really fit very well with the approach that Bryden Wood have been developing with their DFMA and sort of more detailed analysis of how you make buildings into manufactured platform products. So next slide. So when we sort of think to the current nuclear industry, it's really clear that the current deployment model and the current industrial arrangements, the interactions that are necessary for projects between all the parties, the project processes, the project development process, the project management processes, and so forth, and the kind of built systems that we're using, none of these are really designed for the scale and speed of the problem that we're facing. So we end up currently with too much risk, financial risk, business risk in projects, and consequently we have not very many customers interested in doing these projects. Most nuclear projects around the world are financed by governments, not customers, and that has to change. And then because it's a small industry and has a sort of complicated sales structure and it's financed by governments and everything, there's really only a few suppliers that can deliver these things. So we basically just don't have anything that can meet the scale of the need that we have over on the other side, which is 2,000 gigawatts in the next 28 years. And that's approximately 100 large sites per year. So this kind of these levels of the problem that I've identified, we're going to go through in this presentation and see kind of how you can design a solution to this entire set of problems, not just a technical solution to how to deliver a structure or a building or some concrete or something. So next slide. So sorry, go one slide back. I just want to point out that what we're doing here is taking a design approach to systematically address all of these challenges. So we're not saying, oh, let's just make some modules and then whoops, the regulator doesn't like them, or whoops, we didn't have a real manufacturing environment to make them, or, this is not a technical solution that we're talking about. It's an integrated system for solving all these constraints. Next slide. So briefly, what would this system need to do? Well, there's a potential $4 trillion market for advanced heat sources. So we first need to make projects cheaper, faster, and have less risk. And that's a lot of what Jamie was just talking about, is ways to engineer out the factors that cause those undesirable things. If we do that, we will drive more demand. So if we're solving a customer's problem and we can turn it into an attractive investment, we're going to have more customers. And as we do that, as we engineer these to have a broader supply chain, lower risk, and faster implementation, we're not only going to have more customers, but we're going to have more suppliers who can play in this market, global market for productized building systems. Next slide. So again, we're talking about a coordinated platform approach that solves problems at the build systems level, at the project processes level, like the whole development process for the project from the customer's perspective and so forth, and the interactions between all the parties that are necessary to efficiently deliver a project. Next slide. So the build systems that we're talking about here are the ones necessary for providing a new heat source for a coal plant. So we're talking about a standardized advanced heat source or advanced reactor built in a standardized building, on a seismic isolation system, with efficiently regulated systems and buildings for the supporting systems, which may not have to be nuclear safety grade, a heat transfer and storage system, which is a kind of USB connector between the advanced heat source addition to the project and the existing coal plant, and then an ability to reuse as much of the existing coal plant infrastructure as possible. Next slide. So the first design approach is to reduce the scope of nuclear systems. And so what we're doing is confining the quote nuclear part of the project to just the part of the project that is the heat source. The rest of it is isolated from being nuclear by the role of the heat transfer and storage system, which cannot propagate accident initiating events back to the advanced heat source. Next slide. This is what that looks like in the kind of physical manifestation at the bottom. Next slide. The second major design innovation is to enable full standardization of the building systems and the reactor systems through seismic isolation. So to use seismic isolation, which is widely used in commercial buildings and even used in some nuclear plants in South Africa and France, to enable the transformation of the differentiated seismic conditions around the world into a standard set of seismic low acceleration seismic conditions that would enable complete reuse of the designs. So no site-specific re-engineering of those systems. Repeat after me. No site-specific re-engineering. That is how you make something into a product. That is how you eliminate the complexity of very long and difficult regulatory reviews. So instead of trying to say that we can make this, please treat our thing as a product, we're actually making the design choices to enable it to be a product, to be fully standardized. Next slide. Then, as Jamie was mentioning, you have a standardized building. The next thing you want to do is really reduce the variability in the execution of that building design. And that means you want everything to be very high tolerance. You want full-on manufacturing of almost everything in the building. And you want a very well-defined, easy, and kind of high quality assembly sequence. So this is really using design for manufacturing and assembly, which is essentially how all products are made today. There are no products that don't use this process. But it means that you are thinking extremely carefully about how the parts are made, how the quality that you need in those parts is assured, how those parts are, stored and transported and deployed on the site, the assembly process for those parts, the validation, the approval of the assembly process. So all of that is something which the manufacturing industry has brought to an incredibly high art, but which we don't use in the construction process. And Jamie's company and Jamie's work, a lot of that is around basically how do we take all the stuff that we have. It's like, hey guys, we solved all these problems in this other industry sector. Let's just see if we can use their techniques and processes and supply chains to make the stuff that we need. So this is really about driving out all the variability and kind of messiness in construction, which makes it risky and slow and brings up problems while you're putting the building together. So the idea is that this set of designs would have a very well-defined, standardized set of parts that can be made by a range of suppliers. And next slide. And so this, you basically end up with modularization of systems. So systems are put on skids and built in factories and then brought to the site. And then factory production of a large amount of the structures, the components that go into making the structures. And a rigorous approach to figuring out which systems are common to all the advanced reactors, or most of them, and which systems require being in a nuclear grade building and which don't, and so forth, and really apportioning that so that you put as many things in commercial grade buildings and as many things being commercial grade systems as possible. This also helps reduce the complexity and delivery challenges. Next slide. So this is how you get a standardized system that addresses a wide range of requirements for repowering a coal fleet, where you're going to have different energy and heat requirements from the existing power cycle. You want to accommodate a range of different advanced heat source providers, and you're going to have different site layouts and local requirements. You need to pull all of that variability and those requirements into your system and have a automated design tool that basically generates a kind of version of the standardized building that is designed in such a way that to take account of those things and to be ready for those variations, just like the road example. Next slide. The second area that we saw in that circle in the beginning is the project processes. And I'm going to go through this very quickly, but this is a kind of a big topic. But basically, each project has to go through a series of decisions and planning processes and so forth in order to determine whether you have a viable project, what's the best form of the project, who's going to be involved in the project and contracting with them, then delivering the project, and then continuing to operate the project profitably. Right now, these processes are, especially these front-end processes of screening and project definition, are very expensive and slow and difficult if you're trying to repower a coal plant. So a typical development process, if you think about what a company like NewScale or the project, the Vogel project, if you look at what they had to spend before they started construction, it's hundreds of millions of dollars, if not billions of dollars. This is a kind of, I like to say that the nuclear industry has come up with the product that is the most difficult to buy of any product that has ever been developed. We need to change that. If we want to achieve scale, we have to make this easy to buy. We have to make it the best thing. You wake up, you look at the options and you go, wow, this is really the best one. It's fast, it's low risk, it performs the way I need it to perform, etc. Right? So next slide. So the first thing that we're doing in our project is developing a cloud-based tool to help customers, coal plant owners, assess the viability of their plant for repowering. So the idea here is that you log into a portal, and we're working on this with Microsoft. So Microsoft is going to be providing software development and hosting for this platform. But the idea is that this would help you make the decision about whether you have a viable project or not, and roughly what the shape of that project should be. So the idea of this tool is to turn you from a potential customer into somebody who's actively developing a project. Next slide. Then you have the more detailed design tools that Jamie was talking about, where we're going to develop tools that will actually do a preliminary design and, in fact, a detailed design of your plant using the approach that we described. And the approach here is we're not going to be doing this. We're not going to become the EPC or the designer. These tools will be available online, and customers will pay to use the tools, and they will be able to design the plants and then contract with builders to build the plant using this system. Next slide. So then there'll be tools to help with the construction, and then also we're talking with some vendors who want to develop tools to help with operation, which is on the next slide. So next slide, please, and next slide. So the idea here is really to develop a tool set that helps customers with project development. How do we make the customer project development thing into something like Jamie was talking about? Used to take $500 million and 5 years, and now it's a weekend with 5 people working on it, let's say. And that's a slight exaggeration, but we want to make this into something that you can do in a year and get through all of these phases, and quite cheaply. And we're doing that in parallel with the development of the advanced heat sources. So when they come through the demonstration projects, there'll be projects ready for them. Next slide. So I'm just going to go very quickly through this part. The idea is that you need all these entities to be involved in making a project successful. And we have now great examples of information sharing platforms between, for business ecosystems where these processes become, automated and where data exchange is happening very easily and so forth. So our plan is to build this kind of a platform to enable projects. Next slide. And this will reduce interaction costs and increase the scale of opportunity, which is necessary if we want to achieve speed and lower costs, but it's also necessary if we want to bring in more participants and increase the scale of industry and scale of deployment. Next slide. So the tools that we're developing, as I mentioned, actually will, each of these stakeholders will have their view of those tools as appropriate. And that will essentially enable a more rapid decision-making and rapid coalescing of this demand. Next slide. So our goal is to have hundreds of projects having made their way quite far in the project development process so that they're ready to begin ordering and installing these heat sources that are being developed by the advanced reactor vendors. And that means the advanced reactor vendors are delivering a standardized manufactured product to a project. So that can be licensed once and then replicated across all these projects because they will have standardized seismic and other conditions. Next slide. So that's how we're kind of attacking this problem to repurpose 2 terawatts of coal in 28 years. And we think we can achieve less than $2,000 a kilowatt all in for the repowering project, which translates into approximately $35 a megawatt hour for the electricity. And this reduction in risk and cost is going to enable many, many more customers. So ultimately we'll drive thousands of projects for these technologies, which means that we're really creating a multi-trillion-dollar market for advanced heat sources, which is going to attract a lot of investment. And as Kirsty mentioned, this is going to mean that large manufacturing companies who know how to deliver things at scale will view this as a big opportunity and invest in this and become the kind of suppliers that we need to really scale this up. So thanks.
Painting this broad picture, and I'm happy that you're coming to this slide because I had some key takeaways that I took from this slide, like what else do we want other than the cheaper, faster, and a less risk project? So every project we want like that. And then this loop, which you showed here, we don't know when and where this will start, where we have more suppliers and more customer. So hopefully this loop also starts soon for the nuclear industry as well.
Well,
one thing
Chirag, we strongly believe that obviously these things are all interdependent, but the part that's missing now is the customers.
Yeah.
So the reason our project is focusing on that is not because we don't need suppliers or because we don't need advanced heat sources. It's because the part that we really need, that we need a lot more of, is customers. So this project development tools are really designed to create the customers, create the demand, to create the pull for these products.
Well, that's what I hope that that was I was coming to as well, that I think this interaction, this needs to be very effective and efficient. And in that case, your tools which you're developing could actually emphasize and facilitate this loop to be, let's say, existent, which is non-existent now. One thing that you also mentioned that with the help of maybe advanced manufacturing and quality control, we can come to a fully standardized product. And then I would like to also repeat after you that no site-specific engineering should be required then. So hopefully that comes also into picture, which will actually help.
A special mantra.
We will remember that. Okay. To all the attendees also, please remember. Okay, so thank you for this. We have, I think, 10-11 minutes for a panel discussion, which might not be a full-fledged panel. I request all the panelists to kindly switch on their camera so that we can have this group view. I have a few questions that I want to ask to this panel. I also took a look at the Q&A session. There are some interesting questions there also, but they have been answered in the Q&A panel. I might pick a couple of them from there. But let me start with this first question. We have been talking about modularization and how it can be advantageous in different scenarios. Let me address this first to Giorgio, and then I request others also to add to that what are the main disadvantages of modularization approach? And could there be situations where a stick-built approach could make more sense? So I would like to start with Giorgio, and then I request others to add.
Thank you very much. So the key advantage of modularization is that it requires more upfront engineering and require a more complex procurement and limits the possibility to change during construction. So modularization is a great idea when you have to make hundreds of identical units, because that really speed up. You don't need to do re-engineering for each unit and so far and so forth. But when you have maybe 1 or 2 units, probably what the empirical evidence shows us is that modularization make things more complex and create more problems than the problem that they intend to solve. We do modularization on car where we sell 1 million car. We don't do modularization on a car that is a Formula One that need 1 or 2 car.
Okay. Anybody else wants to add to this? Some insights?
Yeah, I mean that chimes with our experience as well. Actually, that one of the things that's held back certainly the construction sector from doing this is that people try this, they don't do it at scale, and they go, I tried modularization, it wasn't very useful, it cost me more, it was more effort, and you go, so they never then get over the hump of sort of trying to do it more than once. But I think Giorgio's right. If you're going to do this, you want to do it, you need, all the benefits come when you start to do this at scale, but the benefits are absolutely vast and definitely outweigh the kind of limitations or the perceived lack of design variability in things, which is not true. No one looks at anything manufactured and says, well, it wasn't designed very well, or it wasn't very nice. No, everyone expects everything else in their lives to be manufactured to a higher quality, to perform better, to be a better thing. And you go, it's that. Why are we not doing that on everything?
Sure.
Yeah.
Okay.
So just,
maybe one comment from Eric.
Did you want to go?
Sure, Eric, please go ahead and then I ask Anthony.
Okay, well, I was just going to comment in terms of, to the extent that you can modularize and standardize the plant, coming around to the supply chain, if you actually don't have that fully standardized supply chain, you're still not going to end up necessarily with a standardized or fully modularized plant. A colleague of mine likes to say, the plant really isn't fully designed until you've actually procured all your equipment, or you know what your equipment looks like. And so unless you actually address the full supply chain and also the way in which the architect engineering firms and constructors work, it goes back to contracting too, roles and responsibilities. Unless you address the whole ecosystem, you're not going to end up with a standardized plant, and the limits, your modularization will be limited as well.
Yeah, I think it's really important to distinguish between, what you might call engineering modularization, which that's how you could sort of describe what Westinghouse did, and what Jamie's talking about, which is design for manufacturing and assembly of the entire thing that you're making, the entire building or building system or whatever it is. And I think that is we have plenty of examples, and the reason we still have debates about modularization is because a lot of modularization hasn't worked very well. And I think it wasn't done in a design for manufacturing and assembly environment. So I want to be really clear that what we are recommending for this repowering coal thing, we would not call it modularization, and we don't recommend engineering only modularization as an approach. But this design for manufacturing and assembly approach can include things which are modules. You'll notice that some of the skids and so forth on our diagrams are modules. So I think it's not really like modules yes or no. It's really, this kind of really thoughtful, fully integrated design, and going all the way, as Andrew just said, going all the, whatever your process is, whether you're using a standard construction or something more manufacturing oriented. In our ETI study, I had a very interesting series of interviews with the people who built the Japanese plants, the Japanese boiling water reactors, in the shortest amount of time that nuclear plants have ever been built. They did a DFMA analysis of their conventional delivery. So every single operation on the site, the construction site, was planned and thought through before the drawings got out of the design stage. So design was not done until you had done all that work. And that you can, I think you see the results of that.
No,
and so that's what's critical. It's not modules versus no modules.
Yeah, no, I think it's very important to understand also when we talk about modularization, what kind of modularization we are talking about, and also the design engine philosophy that's there behind it. So I think it's a very valid point. So let's continue this thought, and let me ask next question to Jamie. In your presentation, you have talked about new approaches to design, which may differ significantly from what things are done today in other sectors, and in particular to the nuclear sector. So what are, based on your experience, the main challenges when introducing new design approaches as the one that you propose? And then we will ask others that, do they agree to that in nuclear industry or not? So Jamie, please go ahead.
So in our sector, what we see is there's culturally, I'm sure the same, there's always a resistance to change because it's the existing business models and incentives and ways of working are geared around the current ways of working. So for instance, if we've developed a design that took us 4 days rather than 15 months, a traditional design consultancy was saying, but I would be having people sitting there for 15 months getting paid, generating revenue. So the incentive isn't necessarily there for people to automate the design process in the way we're talking about. Our response to that is, but if you look at the amount of design that needs to be done in the next sort of 30, 40, 50 years, UN predicts another 4 billion people coming who need healthcare, social infrastructure, transport infrastructure, all these things. There's so much work coming. There's so much design to be done. Our view is if you don't automate the design, you haven't got a chance of getting enough design bandwidth in the industry to test all these things. And that will be the death of good design, because you'll end up either doing a bad design or cookie cutting things because you haven't got the time. So our response is the only chance the planet has got of keeping up with the needs of the next 4 billion is dramatically increasing productivity in terms of design, delivery, carbon reduction, all of these things. So if we don't start adopting this at scale, you all know this, the scale of the challenge is too vast. It's too late to tinker around the edges now, we think.
Oh, thank you, Jamie. Anybody else want to add to what he said could be the challenges that we could face?
Well, yes, I made a brief allusion to this in my opening remarks, which is that we need a kind of different way of thinking about the structure of these industries. And when you look at something like the solar industry started out with a very kind of clunky vertical orientation organization for delivery. In fact, when I started in the renewables industry, you went to a single company that had an R&D department, had a cell manufacturing line, had a module manufacturing line, had a project engineering group, and had a sales group developing interest for projects. And they would deliver you a solar project for your cell tower, or whatever you needed it for about $10 a kilowatt. And we now have large scale, horizontally organized industry in the solar industry with, module manufacturers, panel manufacturers, support hardware manufacturers, and technical integrators who bring that together in the form of delivering a project, and then project developers who go find the projects and contract with that supply chain. And the fact that you have this horizontal organization with people competing across the horizontal slices of the chain is what makes that industry able to reduce costs and increase scale so fast. So My suggestion is that we need to kind of look at what has worked. And that's basically how almost all major industries have achieved the scale that and cost reduction that we've seen. So there are obstacles, but as Jamie said, there's a huge opportunity. And we think the kind of theory of change is it's likely that new entrants will come in who can perform one of these functions very cost effectively and who see the scale of the opportunity. And so it's not necessarily existing EPCs or existing nuclear companies that are going to be able to do this. They're going to partner with new entrants who have kind of already developed that kind of capability and scale in some other industry.
Okay, no, thank you. Thank you very much, Eric. I think we all agree, and I think the whole idea for this workshop is also to understand how we can actually learn from what has happened in the other industry and try to bring the efficiency from that industry to our industry. And also, I think the example of renewable, how they have also scaled up could be a very good example for us also to learn from. Okay, with that, I think there are several other interesting questions that I have, but I have this thing with the time that I try to keep things in time. So with that, I would like to thank all the panelists for all their time today for this interesting presentations, as well as these interesting discussions that we had during this short panel. I hope we had more time for the panel, but as I said, we are always pressing against the time. So I give the floor back to Antonio. I just took 1 minute extra. Thank you very much, Antonio.
So thanks a lot, Sirayo, and all the panelists for these interesting discussions. And now, let's say that after this panel, we have like a clear view on what are these, could be these new deployment pathways. It's about getting into, I would say very briefly, a product-based approach. But again, even if we want to get there, we still need to meet, at least for the nuclear part, the regulatory expectations, new ways to regulate it, innovations. Also, we need standards to scale up all of this. With this, just moving towards the end of this workshop, I'm extremely delighted to have now with us Mrs. Sama Bilbao y León to provide some closing remarks. You all know her, but Sama Bilbao y León became the Director General of the World Nuclear Association in October 2020. She has more than 20 years of experience in nuclear engineering and energy policy, very diverse professional experience working in the industry, in academia, and international organizations and fora, such as the Nuclear Energy Agency, Generation for International Forum, and the IAEA. Please, really, Sama, the floor is yours for these closing remarks.
Well, thank you very much, Antonio. Thank you very much, Diane, for the invitation to join you for this workshop. And again, thank you very much to the OECD Nuclear Energy Agency for organizing this workshop and bringing the insights of such a diverse set of stakeholders, because it is very important to show how the nuclear sector is building capabilities and developing and incorporating innovations to nurture the learning curve that we need to have to progressively reduce the cost of new nuclear power plants. So, because, you know, let's face it, if we are serious about meeting the climate change challenge with the urgency and at the scale needed, we really are going to need to actually use all the energy sources that we have at our disposal, all the proven energy sources that we have at our disposal. And a very important thing is we need to do that in a just and equitable manner, making sure that we don't leave anybody behind, whether it is at a sector level, as you have explored today with the fossil fuel industry, the coal industry, or as well as a country level, as we are looking at emerging economies. So of course, the role of nuclear energy is going to be essential in this sustainable energy mix. And frankly, as we are seeing more and more, certainly in these recent times, there is the added element of energy security and energy independence, which of course makes nuclear energy even more attractive in this overall equation. So for all these reasons, it's super, super important to keep the focus on reducing the cost of nuclear, because there is an increasing number of countries that are considering new build decisions. I'm not going to name them all. France, the UK, Poland, the Netherlands are some of the examples in Europe. And we have heard also of new build projects in Canada and elsewhere. So in that sense, thank you very much for organizing this excellent workshop. And now I am here left with the very difficult job to pick up some of the highlights, some of the key threads that we have heard in the last couple of days. So in the first session, we heard about the experience from recent large nuclear projects. So we did see about some of the difficulties that we have experienced in projects in Western Europe and North America. However, this session did confirm that the industry has drawn the lessons to reduce the cost and the risks for new nuclear projects in the near future. And again, we did see how the Western industry has revealed its capabilities, the supply chain, and really the know-how to be able to reduce the cost and the uncertainty in future projects. So we saw how modularization, which is one of the key elements of small modular reactors, can be applied just as well to large reactors and can improve the constructability. And then the other thing that we saw that is very important, how construction techniques need to be supported by a robust project management, but reliable supply chains, and also the important contractual strategies that are going to optimize the distribution of the construction and also the financial risk to truly yield the expected results. So in the second session yesterday, we had a very great overview of a large number of innovations in nuclear construction and manufacturing that could support additional cost reduction in the relatively short term. So one thing that I think is very interesting, how we continue to make progress in achieving full data continuity between the design phase and the construction phase. And of course, this would also be extended later towards the operation and the maintenance phase, which will not only improve the cost during construction, but in the longer term for the operation of the units. So of course, this is resulting in higher automation levels and hopefully lower construction risks. We also saw a few techniques such as steel plate concrete structures that are already proven in other sectors and also in existing nuclear designs. We have seen this being used already successfully in China, in Korea, in Japan. So it's important to see how these techniques and others are being used, continuously expanded, and continuously improved. And of course, again, these are useful for both large reactors and small modular reactors. Today, in session 3, we explore new construction and manufacturing techniques that perhaps are better suited to small modular reactors. So for example, we saw that with smaller power outputs, and perhaps because it is possible to expand the number of commercial grade components, or even to reuse part of the existing infrastructure, as we saw today for the coal repowering case, there are additional opportunities for the improvement or the cost effectiveness of these projects. And we did see also today how the nuclear sector can continuously learn from other sectors when it comes to innovative construction approaches. So we discussed today some examples from the aviation industry, from the shipbuilding industry, or even we extracted perhaps some suggestions, some ideas from the furniture building industry from IKEA. So that was quite interesting. Another thing that I thought was quite important was the fact that we do have quantitative analysis that are supporting the benefits of small modular reactors in terms of its constructability and how that is going to translate in lower costs for construction, but also for the overall levelized cost of electricity. But let's be realistic. We still have uncertainties. And in this sense, I think that we all may agree that some demonstration projects are still going to be necessary to truly validate these economic estimates and to actually help us improve these estimates. And then in the last session, which was also super informative, we really learned how new construction and manufacturing techniques, they have to meet regulatory expectations, and they really need to follow the codification and the standardization processes in order to be able to deploy them at the scale. So of course, this process sometimes can be lengthy, and of course, in any case, it will benefit from collaboration and the early engagement among all stakeholders. I think that we just saw this in the recent session, how it is very, very important to make sure that the developers, the research and development organizations, the industry have an early engagement with the regulators to make sure that this is a truly iterative and very, very effective process. Then the other thing that we saw is how many of these techniques that are still not fully codified in the nuclear sector, they offer enormous opportunities to collaborate from the beginning. So perhaps we can achieve higher levels of international harmonization from the very beginning. So let's try to harmonize these new techniques before they truly get incorporated in the more complex standards and regulations that we have at a global level in the nuclear industry. So in this sense, I would say that the work that the World Nuclear Association Cordell Working Group is doing is quite useful, because they are very active on this field, and they are currently developing proposals for international frameworks to streamline international licensing and regulation. Because let's face it, I think that the licensing and regulation of small modular reactors is going to be essential if we truly want to achieve the business case of small modular reactors that truly requires a global deployment of these technologies, so that we can really make the most of these economies of series that we are discussing. So in summary, I would say that really most, if all of this construction and manufacturing innovation would really not be as effective as we want them to be without new projects. So this is why the timely decisions on new build are absolutely essential for the nuclear sector to seize these new opportunities. So I think it's very, very important for us to have a long-term plan for continuous construction projects, because let's be realistic, the best way for us to get good and cost-effective at building nuclear power plants is, of course, building nuclear power plants. So this is why a lot of these improvements that are very much ready to be used, and in some cases we are already being used, but we really need to truly make sure that they result in cost reductions, is for us to have a predictable demand coming up and somehow long-term visibility on upcoming projects, so that the nuclear sector and the associated supply chain can be stood to deal effectively with this demand. So as we heard today, there is a need for both a push and a pull in these new projects. So for example, I think that investment in supply chain capabilities will require assurance of the long-term energy policy commitments for new nuclear construction, because otherwise it is going to be difficult for the industry to adopt the latest technical and organizational advances in the most optimal manner. So really, the new build ambitions need to be adjusted to integrate both the supply chain constraint and the demand to ensure the continuously ability to enable this development. And then the other thing that I think is very important is for those countries that are considering a new nuclear program or to expand an existing program, it's very important to commit to a standardization. So it would be good to commit to multiple new build projects, commitment to standardized nuclear programs, and to try to capitalize as much as possible on the serious effect multi-unit construction, and also to have this continuous design and process of optimization to really make the most of the lessons learned to truly effectuate cost reductions. Finally, I would say that financing remains a key challenge, but I truly think that as new projects come online, and we see that all these learnings and all these new technologies and all this innovation are positively implemented, we are going to see how the financing risks are going to progressively vanish as we provide more confidence and more trust in the financing industry. So in that sense, I think that it is very, very important to have a concerted effort among all stakeholders. So I think that governments need to create an environment that fosters both the social contract and with industry and with society to truly achieve this nuclear construction reduction in costs. So because let me just finalize by saying that overall cost reductions can be unlocked thanks to these new construction and manufacturing techniques that we have seen throughout these last 2 days. And these techniques are going to be able to foster nuclear development and certainly support the very ambitious climate change targets or climate targets that we have. And for that, nuclear capacity is going to need to grow to more than 1,200 gigawatts by 2050. And this is based on the IPCC projections and of course based on our World Nuclear Association Harmony goals. So this means that by 2050, about 25% of the electricity demand needs to be met with nuclear electricity, but more importantly, or just as importantly, nuclear can contribute to the decarbonization of other sectors of the economy that are difficult to decarbonize. So we talked about industry process heating and cooling for buildings, hydrogen production, transport, shipping, etc. So as we saw today, the nuclear sector has been able to deliver fast and deep decarbonization in the past, and there are frameworks that we have explored in the last couple of days that are going to be able to make us take advantage of these technologies to scale up fast and deliver the abundant, reliable, affordable, clean energy that we need to tackle climate change challenge and to deliver the sustainable development goals. So hopefully the nuclear sector will be able to take advantage of everything that we have learned in the last couple of days in these workshops. So thank you so much. Back to you, Antonio.
Okay, thank you, Sama. I don't think there's a better way to finish this workshop. Thank you for the comprehensive summary. And also thank you for your presence and to provide this, let's say, global view on the industry, how can get better and can help to meet also climate targets. So with this, I would like to close this workshop. Also an opportunity to thank you all again, and also everybody behind the scenes that make this thing possible. And again, it was perfectly highlighted by Sama, but the importance of what we have shown is that how costs can be reduced, how discontinuity can be detrimental in specialized skills, how the concept of the series in any form, large, small nuclear, is just key to improve the construction approaches and to create the effectiveness and industrial effectiveness to reduce the cost. So thank you so much, everybody. The NEA will continue to work on this topic, and I wish you a nice and great evening. Thank you all.